I want to talk about this. I'm going to go through it somewhat quickly, but it's a good thing that we could ask some. I don't think I put questions in PoCS about this, so maybe I did. I'll look at that. Questions for Starbucks. But there's been this sequence, and I just want to put this in. I will go through it somewhat quickly. So we've gone through a sequence of things like just Murray's law at the branching of a pipe, right? I mean, or branching of tubes. You know, really basic kind of optimality structures at very, very small scales, out to the single source to many sinks kind of thing, or you can think of this in various ways. Or many sources going to one sink, which that's a this is a hard thing to do for a lot of things, right? If you just have one source and you're in 3 dimensions, it's hard work, right? That's hard work, right? So when we get to certainly the scales of a continent, we're going to have to break it down. And indeed, when you think about river networks, that's of course what happens, right? It's actually a whole bunch of basins that drain off continents, right? There's not just one big outlet, unless you're Australia and you just don't have any. Because you're very old, flat, and you've given up. It's okay. Let's see. Okay, good. Yep. Look, let me just add one more thing. This braiding versus non-braiding thing, really profound thing. There was a paper, I did reference it in the slides, but it's the Banavar team again. They did another thing in 1999, which is it is a very nice paper, and they've proven it sort of a different way that if you have some impedance story, again, there was that kind of current to the power of gamma, depending on that exponent, you would go from having loops, the way they thought about it, having loops in the flow versus non-loops, which is that distinction between braiding and non-braiding. So that's really very cool. Of course, famously electrical circuits, right? They have braiding in them, and are essentially, and we'll see this later on. Current running through an electrical circuit matches up with random walks, which is kind of an awesome thing. So cool. Which we'll use to find communities, which is really strange, right? Yeah. That would be really fun, actually. Okay, so, okay, all right. So, I mean, this is just so much fun to talk about. So we're going to have lots of things now, lots of sources and lots of sinks. And we'll think about it 2 dimensions. You could have higher dimensions, but this is a big deal for us, especially as sort of humans, like running around trying to, get out little packages from Amazon with nice little things in them, and or whatever it is, and or our little packets of information, right, that come through, your little Instagram post that makes you happy, right, little pellets of, because that's what we are now, with little information receiving objects. We've had to build really interesting things. Okay. Oh, Amazon's trying to do this now, right? Amazon's starting their own delivery service. Is that true? Yeah, like to compete with UPS and FedEx, whose stocks sort of went. All right, so, okay. Right. So, good. I have to stop myself from talking about other things. Okay, so we're going to have uneven population densities. And we understand why that is, and I think there's still work, we were talking about this the other day, to like, maybe there's something quite beautiful way we could figure out the people are distributed in some way optimally based, and maybe it's just at different points in time, based on the geography, right, of the landscape. Because rivers will matter, mountain structures will matter, and so on. So people, they only live in certain parts of the world, and they really tend to clump together. Of course, there's been more of a movement to cities, famously. I don't know, yeah. But generally, the way we'll think about it is you think about these problems in the human world is that we have people distributed in some way, and that's just fixed, right? And so against that background, how will you now put down hospitals and Starbucks and so on, right? Oh, what else do we have? What are the things we have? CrossFit boxes. We've had to add them as we build our little religion. Totally a religion, actually. Yeah, really, really good. Yeah, because they're a test for religion. Like, would you let people in your group like look after your kids? Would you borrow money from them? Would you lend them like all these little sort of, and he was like check. But Danforth says no, it's not. Okay. So anyway, he's fine. He's above it all. Okay. Let's see. So okay, so we understand this, right? So if we had people just distributed uniformly, then we distributed out. We'd have to put our Starbucks in uniformly, and so that's true in places like the suburbs, right, where it's translationally invariant. And I remember driving through, I think, places like Orange County, and I think it was somewhere in Cincinnati. Like, the same stuff comes back every 3 or 4 or 5 miles, like another mall, and the same things are in it. And it's just like, did I go in a loop? And no, it's just, you know, and there's no structural whatever. You know, you're kind of in trouble when people start giving you directions. They say, go to the first McDonald's and then turn. Like, it's not the beautiful tree or anything. It's now like referenced by fast food structures and large boxes. You're like, and I'm always like, no, don't tell me those things. But of course, now we have little magic rectangles that tell you where to go, which we obey. Okay, so we understand that, and right, and in fact, you know, that makes it easy. Just put another mole there. So that's a hexagonal lattice because it's awesome. 2 dimensions. We can talk. We've talked about it in parks. We had a lot of fun with that in parks. But it is a very special lattice. It's the only regular lattice that feels like you can't feel the lattice, right? So if you had a big triangular hexagonal lattice and you squeeze it, it feels like it's just one big uniform shape. But if it's, you know, square, then you can find the structure matters. So you should do all your simulations on a hexagonal lattice. It also justifies Settlers of Catan and checkers, Chinese checkers. Okay, so all right, so population density is absolutely incredibly uneven. I mean, here's an example. This is from Gassner and Newman, and yeah, people are really banked up on the coast, of course, and then away from the Rockies. So I'm just going to tell you, and this is just revisiting this quickly. I just want to talk about it quickly. There aren't a bazillion slides. I might skip over the Stefan stuff. Okay, most fair, right? So you want. There are a range of things, and the work that we'll get to eventually, as you'll recall, is somewhat recent. It's only the last 10 years that people have sort of added to this, but this is a long body. People have been thinking about this for a long time. I'm sure it goes back 100 years, but you have geographers and mathematicians and computer scientists, like all solving different kinds of problems, but basically the same thing. So this is the idea of this is hospitals. So you're trying to, in this case, you might want to have the average distance that anyone has to the nearest place is as short as possible. Okay, so we've got some uneven region. This is the basic thing, and again, this is just to refamiliarize you with this. There's some density underneath it, some population. We've got n things we want to put down. And then this first game would be minimizing the average distance. So you can see you could do this with like a simulated annealing or some sort of optimization thing. You've got this fixed structure, you throw it down. So this is the results. Again, and these are just great papers to have if this is something that comes across into your vision, something you have to think about at some point. This is putting 5,000 facilities down, and against the backdrop of population which was from the 2000 census, right? So of course you can't see these things properly, you know, when there's enough density, it's like, you know, it's really stacked up, it's not shown here. But the cells, again, so each one of these little blue dots is a facility. There's a population that's not shown, but in the background there's going to be some population of people here. And so what's really happening is this equalization of things, right? So that there are less people here, so you know they're going to have to travel further, which is a bit of a problem. But they don't count quite as much, right? Because there are just less of them. So there's going to be this balance of things, and then you also have things about you don't want to overwhelm places, so that's a problem as well. I don't know if that's in this one. You have to think about, what's the maximum number. It's not really in this one. You just make a bigger hospital because it's really just the distance. All right. So that's an optimization thing. And if you look then at the local density of people, again, this is prescribed and fixed in this case. Of course, it changes over time, and that's an interesting thing. And then the density of these facilities, and then plot a regression, you get rho to the 2/3. So it's a bit of a funny, you have to think about this a little bit. It's density of facilities as a function of density of people, and it scales as a 2/3 power. So fits pretty good. Of course, we are, and I'm going to use this notation, facility and population. They've got rows and big Ds if you go to the thing. Good, looks good. And so it's a 2/3 power, right? That's what you think, that's what you guess, because you want it to be explainable and you want to go for the simplest thing first. So little d in this case, right? D equals 2. So 2 over 2 plus 1. So that would be a bit of a game we'd like to get to. And indeed, that's the story, right? There's a very different story to branching networks that we had, right? One source, one sink, and then many of the other kind. Now they're distributed throughout a region. So it's another kind of optimal thing. The network structure will go on top because then you want to think about how do you get between these. So, for example, we could have our sinks or our facilities could be airports, right? So where do we put airports so that people can get to them reasonably well? But how do we also then allocate them so they can connect fairly well between each other? Hopefully this is not too bad of me to say this again. So I just want to point to this one. I'm going to skip through it, but people know about this paper, I guess. But again, this is a science paper. I mean, it certainly got a nice big billing at the time. I don't know if Stefan is still around, but he's an interesting character. I know I talked about him in PoCS. Sort of a story that he seems to have been. He was a sociologist who was kind of like looked down upon, I think, by his fellow sociologists. He had some struggles. He was interested in the internet, and they said, you should not. It's not the web. And he said, no. He was told not to work on that. This is in the 90s. It's really true, actually. I mean, he's not the only person. There are a number of people like that who were in sociology or those sorts of departments, like especially young people coming up saying, oh, this is really interesting. We should study what's going on the web. And people say, no. Number of stories like that. Okay. All right, so it's a nice argument. We're not going to go through it, but it has some issues, but he was able to derive this sort of thinking about one location. But there's a better one, and it's really Hussein Zaid, I think, is the first place, but we'll see this Newman paper does it well. This is an interesting thing, and so Michael's been working on this a lot, doing beautiful things. So it's going to be connected to what we just looked at. So it's a little excursion. Just to remind you again, cartograms. And there are, I think actually it's funny, like we've gotten to a version now where we have the square map, everything gets represented by a square, and that seems to be helping for a lot of the visualizations. It's been a really interesting transition, and maybe hexagons as well. So the 48 states plus Alaska and Hawaii will be these just squares, and that's reasonably, you can see it's the U.S. And for things like who voted for whom, and right, things that you don't necessarily want to have population showing, or more importantly, say the actual physical size of the state showing, because it's misrepresenting things, then they're much more powerful. So we've used them as well. They're very nice. But there's sort of been a long struggle in geography and cartography to represent things well. And so here's a game where you do diffusion based on something. So this is population, right? So you basically take the original map, then you sort of uniformly distribute a population, the actual population across that thing. Put in the oceans, you put in the average population for the whole map, if you like. We'll leave Antarctica alone, and then just let it diffuse, right? So India would start off as a bigger blob, and it's going to push out, and then and so on. So somewhere like Canada gets squeezed, right? It has a lower population than the oceans around it and the US in terms of density, so it's just going to get squished as things kind of move themselves around. Indonesia, it's a huge place. It's going to really expand. Australia's going to show how big it is. So these are still they're very distorting, but they keep the one thing they will do is keep the boundaries the same, right? So this border, that if you that crossing there is the same as it was in the original one. But it's diffusion, random walks. It's very nice. Again, just pop through it. I showed you these things. So things like child mortality. These have been these have become somewhat powerful for people to, right? Spending on healthcare doesn't work. And you see Africa disappears in this case. HIV. So these are really, there's some potency to this. Okay. But the idea of this is, so I think this becomes a profound thing. So if you take that original map that we had from Gassner and Newman and then apply this diffusion to it, if you diffuse in the right way, then you see that all of these little shapes are about the same size, right? So it means that you've kind of figured out what the underlying balance of density of facilities is relative to population. And so, so this one is where we've equalized based on just population density. So we've let things diffuse. So these counties that were in the middle of, like the Rockies and some of the Midwest that don't have as many people in them, they're going to get squished. And these big, the coastal ones will spread out and become larger. But this ends up with a bit of a strange looking thing. I mean, the details aren't very easy to pick up, but it's not normalized properly. Whereas if you say, well, let's instead allocate to each little facility area the density of people there to the 2/3 and then let that diffuse, then that equalizes, right? It ends up being a nice thing. So the bigger story, and hopefully we're going to have some beautiful things to show eventually for this, is that there's this idea of equipartitioning, so that systems, complex systems of all kinds, end up being equally partitioned in some way, right? So the simplest, this is not a complex, but you've just got water in a container and it's going to end up being flat. You just leave it there, it'll flatten out, and so there's no, it's in equilibrium, right? And equilibrium is such a profound thing in natural phenomena. It's been a big driving piece in science as we quantify things and understand things. Like the gas in this room is sort of in equilibrium, kind of in a sense, like it's moving and so on, but it's not. And then we have this idea of many systems that if they get bumped away from it, they relax back to it. Many complex systems are, depart from that because they're driven, right, in some way. There's energy being pushed in and it's moving in some way and it's doing something interesting. But it seems even then that if you look at it in the right way, like the hot model, for example. So the hot model, we have this very uneven spread of these fire breaks around regions of forest. But if you calculate the risk, right, the risk, which is the probability times the amount of damage, right? So the big area out here, if you recall this, and I know I'm just making, right, the probability of a fire out here is very low, but the risk, but the damage is really quite bad. So the risk is, whatever it is. That actually, once this whole thing is kind of in equilibrium in a sense, is that the risk is evenly partitioned. So it seems like we should be able to kind of move up through sort of a series of arguments, away from something like just plain equilibrium where it's like an energy balance or something like that, to something, a system that's being tested, like evolutionary systems, engineered systems, that end up being balanced, but in terms of, say, risk. I don't know, that seems like a really profound thing. We'll get to it. Okay, so I can come back to this, and I just really should just show you pictures. So what you would do is this, we're going to minimize, so lots of these optimization things. We're going to minimize this big functional, which is, we're just going to integrate over this whole region, like imagine the US. We don't want the density in a little cell, and then we want to find, well, what's the minimum distance from people in that cell to the nearest facility, right? So there are n of these, so in that case we had 5,000 for the actual example. So we just look at all the nearest ones, and of course it's, you can kind of see it visually. But it's a bit of that's a bit of an ungainly object to deal with, and of course we can't do it exactly. But there are some really clever things. So Hussein Zaid is the person who originally did something here. That paper is from 1982. And see, it's a geography piece. Yeah, awesome. All right. So you don't have to worry about all the words. So basically we're going to have a cell, we're going to have a facility in it, and then there's going to be some area for that cell. And we've made a Voronoi diagram as a result of putting down, right, as we put down these, right, we're going to try our facilities. So sad. All right. We're going to try our facilities. We'll put them down. Here's we'll put boxes for facilities. We'll put them down. And then you come along and you say, well, we start to draw these lines, right? These will be part of the Voronoi cell. So anyone who's here on that side of that line will go to that facility, and they'll go to this facility, and so on. Fair enough. So that's why we end up with these cells. It's always this kind of line between, it's a bunch of lines between, that equally partition between these two facilities, right? So you construct a Voronoi diagram. And then there'll be an area in here, and let's say this is X, this is the ith one, and this is location xi. There's some area for this, and this is just some point in here, x. We'll have some area function which is constant throughout here. If that makes sense, right? So if you're any point in here, then this function is just returned. So you go to a point here and you ask this, you measure this area thing, it will just return you the area of this cell you're in. And that's a nice function to have, right? Because roughly that to a power of a half, that area to a power of a half, is going to be a measure of the typical distance from any member in that cell to the facility. So that gives us something. So we've got a distance piece. And then we do something, so that's our cost function, right? Instead of having a minimal thing in here, we're going to put this area function here. And then there's this clever thing. This is quite nice. Again, I'll skip through some other pieces. This is quite a nice thing. So we have, that's our thing we're trying to minimize. And then we realize that we can do this as well, right? So if you integrate over the whole area and you take 1 over the area, if you break this down into integrals over each little facilities region, then this is a constant in that region, and you integrate over it, so you get area over area. There would be a 1, and so you go through every region, and there are n of them. So this is a way of getting the constraint that there are n facilities. I don't know if that makes sense. So if we, right, so a of x equals a constant. This equals a constant in this shape, right? So 1 over a of x is also a constant, equals constant as well. So the integral of 1 over a of x, and let's call this like gamma of omega I. So the integral of that thing. This is going to be dx, like that. This is, it's just whatever, let's call it, this is 1 over ai, right? It's the area of the ith. This is the ith facilities service area. I want to write that. I want to write words. Sorry, it's embarrassing. Facilities service area. So this will be, that's supposed to be an A. So this will be 1 over, this is just a constant. And then we just have the integral over that area, which of course is AI. 1 over AI, so that's 1. So we get 1 for each one of these regions, so we sum them up and we'll get n. So why are we doing that? It means that now we can write this down. That's the thing we're trying to minimize. This is a Lagrange multiplier type situation, and this is our constraint. We put out lambda times the constraint, so which we'll write as something equals 0. So it's the integral over this inverse area thing has to equal this n. All right. It's calculus of variations, lovely thing. You go through it. Essentially, you differentiate with respect to that function a, blah, 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 and you get this result, and you get out the 2/3 relationship, right? Okay. So there's something to look at maybe later on if that is a problem we put in. All right, good. So then there's global distribution. And this is this little picture in the right-hand corner. So now we say, well, all right, now we need to move our things. So maybe they're people on planes. We have the cost of traveling along a line, like how much does it cost for you to travel along one of these things, and then how much does it cost for you to go through a hub, right, a connecting piece. And so the way this is done is in this paper by Gaster Newman is to sort of just put a balance here, right? So we're going to say this is the length of a trip for a particular section of the trip, and then this is the total number of hops. So you can dial this between, if we put delta equals 0, we're only worried about the total distance. That's the pain, essentially, right? So if you're driving across the country, you're not really worried about all the towns you go through. But if you're flying, then you'd want to turn delta up a little bit, right? And that's manifestly sort of built into, you want to go to a trip somewhere, like no stops, 1 stop, 2 stop, right? Like it's really a big deal to people. So it's made easy, and when you're looking for a flight, it'll have that option. But you wouldn't do that with towns, right? You wouldn't sort of have that. So and then of course then you only listen to your little rectangle that tells you where to go. So you can dial, and so if you have delta equals 1, you don't care about the distance at all, but you do care about each place that you end up in, right? Because you're going to be watching TV on the plane, so it's okay. Or you love planes, you just love them, yeah. Okay. Or whether you have a peacock or not, right? That would factor in there. Plus delta times number of peacocks. Okay. Really one of the great achievements of humans. So, this is all we have for this simple idea, and then you go and simulate things. So this is the network for redistribution if delta equals 0. This is where you don't care about how many places you go through, and that starts to look much more like a road network. Of course, in the US it's been very gridded on purpose, so there's not so much of that. As you say, the hops start to matter, and this is going to be a fractal thing, so there'll be just all these tiny little, it's only showing the top level parts of this network. Then at this, and this is some point, what does delta mean here? Well, it's just a parameter to play around with. So you start to see hubs appear, and they're hubs that really are hubs for airlines, right? So, and in fact, what airlines have done, what we've done with flight is we've approximated a fully connected network, right? What we want is, what you'd want, and this is like Elon Musk, who's clearly a pretend made-up person, you just waiting to be an evil genius. I mean, the name. I know, Afrikaners, they're funny people. We talk about cricket a lot. But anyway, so, you have your thing, you just walk out and you get in your little space pod thing and you go, boom, to the place you want to go, right? So that's a fully connected travel network. You just put it in and you go fly and land. So that's a very expensive, difficult thing to have, right? Especially if it was like tubes everywhere, that would be really difficult to do. Now, you can if you start to build hubs, then really you're approximating with many, like an incredibly sparse version of a fully connected network. So, and you can get to certainly within a short distance of most places in the US on planes, by just maybe 3 hops at most, right? You can get a long, long way. Plus you get to be on a plane, which is fun, right? Magic cylinder, tube in the air, where you just sit in a chair and somehow it all works. Magic flying cylinders, right? So, but that's what that's doing. And there are a lot fewer connections than you'd have if you had everyone, right? N choose 2, 300 million choose 2. If you wanted every person to be able to go and visit every other person, including you'd have like a plane that took you from one room to the other in your house to visit your sibling. So that would be silly. But, yeah. Anyway, so once you dial it all the way up, at least according to the population density at the time, or distribution at the time, 2000, Cincinnati, Ohio is the center of the universe. Cincinnati people here? Do we have anyone from Cincinnati? This is, of course, Atlanta, this is a big hub and so on, and I think Memphis was back here, right? Maybe? No. One of them's there, like FedEx or UPS, they have big hubs in these places. All right, so that was cool. So this is the supply to the most, and I guess this is where we'll get to, supply to the most. So this is more of the coffee thing. Now you're not trying to save the world. I mean, you try to make people happy, kind of, but also while making lots of money, so it's a little complicated, You make nice ads, but you still want all the people's money. And so you are probably not going to put a Starbucks out in the middle of nowhere, right? Yeah? You're just not going to do it. So that's okay. So this is a public versus private story, and this is work that came out of South Korea. Again, it's right, PNAS 2009, so it's within the last decade. It's been really interesting. I mean, a lot of things I think I've showed you in both, PoCS and, I mean, work just keeps coming along, right? It's not completely done yet, So this was cool. And so they say, well, this is Umadel, they say, in fact, all of this stuff makes sense, but there's just been this kind of one criterion, which is making the average distance as small as possible, which is a very reasonable thing to do, but maybe you just want as many people in the door as possible, right? So if you have one facility, then you're going to put it in the middle of New York City. If you have 10, you're going to really put them in cities, right? You're going to do that, And as you add more and more and more, you're going to end up with things like McDonald's that are opposite each other on the streets because they're franchises and it's really a real estate company and bad things happen and so on, right? So, but you will, right? You'll end up with a block that has 4 Starbucks on it in a really dense city. And people get upset, except for the people getting the coffee, right? And then the other people getting the money. So they point out, well, this is not completely universal. They have these sort of 2 end limits, and one is the for-profit version, which is going to be, you will really actually lay down things according to the density of. And I mean, if you got really excited, you put too many, right? Which I think was kind of achieved maybe in Manhattan around in the early 2000s, where there was just this proliferation of banks and like everywhere along Broadway, there was just like a bank every 3 doors, and there were also drugstores. Which in Australia is a pharmacist, because drugstore just doesn't sound like, it's just confusing. Okay, so really, you want to disambiguate those things. Okay, so, and then they all died, a bunch of them died out. They had a little war where they just went, CVS just put in like, store everywhere, and so did Rite Aid or whatever, and then a bunch of them gave up. It was very strange, but I think they over-densified. Anyway, so they have a nice thing. They say, well, okay, some examples, like that one over there is public schools. It's more 2/3-ish. Maybe it sort of picks up as the density of people goes up. I mean, of course, this is not, this is 2 orders of magnitude. It's not much, but maybe it deviates. Sort of plausible, right? Super dense, so now it's out of control. And that happens in, places like Manhattan where you're building up and it's more complicated. This is for ambulatory hospitals, which is weird to me, but anyway, this is, that's more like matching the density. That's the break-in scaling. Yeah. All right, so they end up with a nice plot like this. I mean, they make a whole table, and when you get to these papers, you've got to be worried that because you never see all the plots underneath, right? That's it. These 2, yes, but who knows about These things, they do have their fits. Yes, they have their fits. That's all right. So you can see some of them are kind of rough. But there's there's a breakdown between US and South Korea. And they kind of have this, these are the ones that are more for profit, and I don't really know why hospitals there. And they have this really weird example down here. So fire stations, this is kind of good, right? I mean, they need to be in places so they can, on average, get as fast as possible to problems. This is a really weird, this is basically zero scaling, right? And this is a government structured thing where they just said they're going to be here, 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 like just pure grid. So this is just really agnostic of any population density. So and of course it's a terrible fit. But the point is that these things are really just distributed in a way that doesn't pay any credence to where people are. Yeah, okay, what else we got in here? Post office for oh, for either of them? I don't think they do have post office. You're right. You're right. It's interesting. And there really isn't obviously there's a lot of, there's somewhat messy fits. They've got this kind of rough transition around 0.8. They sort of, they generally kind of make sense. But this, this is, instead of just one thing, they've got all this stuff right now. So it's much more, they realized it was more complicated and showed it was more complicated. They did a similar thing. They did the restructuring stuff. So, or maybe they didn't do the diffusion thing. But this is, give you a sense of the Voronoi cells, the locations of things. This is the public schools and the hospitals. These ones are going to be, so the hospitals are more clustered in around where the population is, and public schools, hopefully you can see that they are spread out a little more. Is that true? It's hard to tell. Yeah, right? There's more structure in here. Yeah? You can see more structure in here? Yeah. More of an effort to help the people? Yeah. Okay. So that's cool. And so they play around with a thing, and I'll just sort of put this up here. This is a thing so we've got populations in cells, we've got the average distance within the cell, so it's related to what the others have done. Yep, don't worry about that. And then they say, well, now there's something we're going to minimize. It's going to be a mixture of this distance. Before that was just to a power of a half. Well, actually it was power of 1, I should say. It was area to a half. And then we're also going to include the population in there. And so the limits will be, 1, we're back to sort of purely social, and purely commercial when we don't care about how far people travel. And so if you go through that, you end up with this, right? So this is ad hoc. This is made up, right? This is an ad hoc little cost function. It's a way of dialing between two limits. It puts scaling, scaling is in there so that when they solve the thing, you'll still get scaling laws. So that's, definitely kind of made up. But you end up with this 2 over beta plus su. And that's nice. So beta equals 0. Alpha equals 1, right? The scaling is, right? So if we have a 0 here, this is 2 over 2, so the scaling is 1. So that matches with this commercial scaling story. So that's good, and it matches with their little micro mechanism, right? So there you didn't care, when b equals 0, you don't care how far people have to travel. That's not part of the cost function at all. It's just the number of people. When it's 1, then we really, we care about it in a linear way, and we get this 2/3 scaling retrieved, right? Okay, so that's maybe an assignment question. But I need to sort out if I shoveled too much into PoCS. Anyway, it's a beautiful body of work. But it does get to this point in time where it is a bit messier, right? This is great, it's well done, it's a bit messier, so we have to sort of, there's still room to clean this up. But they definitely opened up the box and said, it's not just this thing, there's definitely some scaling like this, here's a little story for it. Okay, so that's pretty good. So I think obviously this is where we're going to end. I will talk about a very important thing next, which is, so we're going to sort of move on from this whole optimal supply networks. We're going to talk about random networks, right? So random networks, again, introduced in PoCS, just an incredibly important fundamental thing that we have to know about networks in general. There are the pure random networks from, this has been sort of well studied in graph theory, which is Erdős-Renyi, but it'll be a departure where we tend to understand that the degree distribution is incredibly important, so we'll fix that and then play with things on top. But we'll get things like bipartite structures and so on, and then some of this nice kind of work with eventually community detection, but also things like betweenness. So they're really sort of right. These are just really important pieces to know about networks in general. Okay. So there's an assignment due this Friday, which is really assignment 3, and there is a new one on deck, and I had the dates wrong, but it's due like a week from Friday. Also, I want to say about office hours, right? They're on now, and they go for sort of an hour, but people hang around, and I'm there, and so you should come along for the festival of office hours, and it's fun. All right, people, thank you. Next time we should have a counting of Winter Olympic things too, right? Like how we're doing.